Hi, this is another video by SM, and in this I'm going to talk about the Norton's theorem and its application in any particular question of the basic kind. I would request you, rather suggest you, to firstly view the Thevenin's theorem video made by me, because it will help you to understand Norton's theorem in a better manner, because both the theorems are complementary. So I have taken the same question as I taken in back for Thevenin's theorem, just for the sake of simplicity and for better understanding, so that we derive up with the same answer and thus we can verify the theorem. See, in the Thevenin's theorem, we were basically concerned with VTH and RTH. That was the Thevenin's voltage, and RTH being the net resistance of the passive circuit. Over here, instead of the voltage, we'll be concerned with the current. So the type of circuit that we will derive from this theorem will be somewhat of this kind. See, over here we'll have a current source for the entire circuit, which we denote with IN, which the suffix denotes the Norton's theorem. That's why we have chosen N as specifically for representation. The next one is this resistance, that's RTH, and this is exactly the same resistance as we had calculated in the Thevenin's theorem. Therefore, I'm not even changing the notation for the same. Over here, the next thing is like this is the load resistance. That is 4 ohm as mentioned in the question. Over here we assume that a current I is flowing, and this is the actual current which is to be calculated. So over here we can see that as we have put this RTH in parallel, instead of being in series as we had done in Thevenin's, we'll have same voltage in both of the loops. So we'll get a formula of this kind: IN into RTH is equal to I RTH plus RL. Now this is because both of the loops have the same voltage, so this is how we have derived this equation. So for determining I, our equation will be IN into RTH upon RTH plus RL. Now over here, we are going to use this formula as the basic one required for solving Norton's theorem questions. After which our next step would be to remove the load resistance that we had done in Thevenin's theorem as well. So continuing with this same question, over here our circuit would change to somewhat of this kind, with the rest of the things being the same. It's just that we'll be removing the load resistance, so marking them as A and B. And this was 3 ohm, 6 ohm, 3 amperes, 27 volts battery, and this is what the circuit is like. Now over here our next step will be to mark the current, the direction of the current. As we can see that we have a voltage source over here, so for sure our current will start to flow from here. So we can mark and assume this to be I1. After which we have over here, we can see that a 3 ampere current is flowing. Over here 3 ampere current is flowing, which will finally add up over here as I1 plus 3. Then we can see that here it's an open circuit. So like I had mentioned in the Thevenin's theorem concept as well, that no current will flow over here. But as we are concerned with the current in this theorem specifically, so we are going to short it. And this is just an assumption, just for the sake of completing this circuit and defining the current flowing in this circuit. So now the current will flow as we have assumed that this circuit is closed. So we can assume that here I2 is flowing, so the left out one will be I1 plus 3 minus I2 in this branch. Over here you can add up to see that as I2 will flow over here and here as well, it will be I1 plus 3 and here I1. So this is how we have defined the flow of current in each one of them, each of the loops. Now our next step will be to define the equations through these loops. Now, as I define the equations, just see, we are considering two loops over here. One is this one and the other one is this one because it includes the resistances. So we can easily define the value of currents. Firstly, let us take this loop. So we can take the direction as this. So we'll have the equation as 6I1 plus 3 minus I2, which is equal to 0. So we get I1 plus 3 is equal to I2. So this is the first equation that we get from this loop. Let us consider this to be loop 2. So from loop 2 we get this equation. Now let this be the first one, and over here also considering this is the direction, the flow of current. From loop 1 we get 27 is equal to 3I1. That's it, because there's no other resistance there. So we get I1 is equal to 9 amperes. So this being the second quantity that we have derived over here. So the next thing is to use this I1 value over here. So we get I2 is equal to 9 plus 3, that's defined as 12 amperes. So thus we have got to know I2. Now our basic aim over here was to get to know the value of I2, which we have actually done. Why? Now over here this I2 is actually the ion that I talked about in this formula, because it's the flow of current that we actually require for defining Norton's theorem. Now the next aim that we have over here is to find the value of RTH. That was the Thevenin's resistance, the net resistance of the passive circuit, though we have done this already, but still just for the sake of better understanding I'll do it again. Over here you can see, like, we'll reduce the circuit into the form in which we find the resistance, and it will be this, which are the resistances left. This is 3 ohm, this is 6 ohm. So the net resistance, that's RTH, will be 3 into 6 upon 3 plus 6. Why? Because both of them are in parallel. So this will be 18 upon 9, which is 2 ohms. So this is the RTH. Now we can easily apply the formula that's here, this formula. So we get I is equal to, IN into RTH upon RTH plus RL, which is equal to the value of IN that we had find was 12 amperes. So it's 12 into 2 upon 2 plus the load resistance was 4 as mentioned in the question. So it comes up to 6. That's 4 amperes, which was the answer that we have already seen while solving the same question through Thevenin's theorem as well. So thus we verified the answer this time. So let me quickly recapitulate it. See, the first task that we had done was that we had defined what type of a circuit do we require while solving a question through Norton's theorem. So this was the basic circuit that was required. This time the only difference from Thevenin's theorem was that we had considered a current source rather than voltage, and the RTH was connected in parallel rather than in series. So this is how we have done. This is a RTH, this is RL, this is a current, and this was the current flowing through RL, which was to be determined. Thus we had obtained a formula over here as voltage in both of them was same, after which we can see we had divided the current sources over here, which you can see, and thus we have received two equations, one determining the value of I1 and further using it to determine the value of I2, which was actually the value IN, which was supposed to be put in this formula. After which we can see that on further simplifying this formula to determine RTH, we have calculated RTH as 2 ohms, and finally putting the values of IN, RTH and RL in the formula, we get a value of 4 amperes for this current. So this is how we solve a basic question using Norton's theorem. Once again, thanks a lot for watching this video.